So it's great pleasure to
Okay.
have Zhihao Duan from KISS. He's going to tell us about the Fermionic rational CFT and the modular linear differential equation.
Yeah. Okay. So first I'd like to thank Satoshi for the invitation. So yeah, the title is Fermionic rational CFTs and modular linear differential equations. It is based on some joint work with Jinbong Bei, Professor Kim Yong Lee, Professor Seung-Jae Lee, and Matthew Sakis. And this is the arXiv number, plus some works in progress. Okay. And okay, I will just do like this. Is it okay? I think it's fine. Okay. So let's first see an overview. Okay, at first, I will introduce some basic results of CFT, in particular rational CFT that are necessary for this talk. And then I will introduce the idea of classifying rational CFTs using modular linear differential equations. I will introduce all the basic elements. And then I will generalize. This is the first part, introduction. In the second part, I will generalize this idea to Fermionic case, to including also fermionic rational CFTs. And then in the third part, I will talk about our classification results for one character and two character cases. And then I will analyze, try to identify the solutions and analyze the properties. In the end, I will conclude this talk by some outlook and a brief summary of this project. Okay, so let's first start from motivation. Well, I mean, to do something, we already need some motivation. So why are we interested in 2D CFTs? So the first thing is that 2D CFTs can describe the second order phase transition of some critical phenomena in the real world. So it's necessary to understand rational CFTs in order to describe those phase transitions. Moreover, for string theories, 2D CFT naturally describes 2D worksheet of string theory. So it's like the basic tool for string theorists. And last but not least, 2D CFTs has very deep mathematical structures, which leads to many fruitful interplay between mathematics and physics. Okay, so that's the motivation part. Okay, now let's talk about some basic results of CFT. So we know that the 2D conformal field theory contains two copies of velocity algebras, which are infinite dimensional algebras as its symmetry algebra, with the following commutation relations. Here, the important thing is that we have a central extension by the central charge C, which is important information for the 2D CFT. And since we have this algebraic structure, all the states are naturally organized in terms of the representations of the velocity algebra. Well, of course, we can have extended carry algebras, but here let's just assume that we have velocity algebra. Okay, and the representation of or irreducible representation of velocity algebras are very simple actually. So they are all given by highest weight representations. We start from the highest weight or highest state labeled by H, which satisfy the following conditions. It is an eigenvalue of L0 annihilated by all the positive modes. In physics, we also call this conformal primaries. And all the other states, they are organized naturally in terms of conformal descendants by acting on this chiral primary with negative modes. Well, this is very simple. And also, if we consider the radial quantization of our complex plane, where the radial direction is time, and the space direction is the S1, what I just talked about actually can be translated into the following language. So the Hilbert space living on this S1 actually can be decomposed in terms of highest representations of those states, where since we have two copies, we have both the holomorphic part and the anti-holomorphic part, with the number D denotes degeneracy. And if H and H bar they are equal to 0, then that means that labels the vacuum of the CFT. Okay. Okay, now let's move on to the most important subject of this talk, which is the torus partition function. we are interested in computing partition function of CFT on a torus. This is so here, of course, is a torus where we identify this side with this side and this with this. Another way to view this torus is that I first glue these two sides, and then we get a cylinder. So we glue this and we have S1, and then we let this evolve in time, and then we identify the two S1s with itself. So this motivates the following rewriting of this partition function as a trace over the Hilbert space with those operators inserted. And then I can make a conformal transformation. I go to this coordinate Q, and then I have this expression. And according to what I told you before, I can decompose this Hilbert space in terms of highest representations. I naturally have this expression where VH and VH bar, they are velocity characters. Here I give you an example of velocity characters, which is the vacuum. So you just do a Q series expansion and you get the whole character. And what's good about the torus partition function is that the torus has a very rich amount of symmetries. In particular, we have an SL2Z symmetry group acting on the torus. It's well known that it is generated by T and S transformations. And the T transformation acting on the partition function is just acting on tau. It just shifts tau by 1, similarly for tau bar. And if you look at this expression here, this means that the states must have integer spins. So this is like a constraint on the partition function. And a more constraining, like a more severe constraint comes from the S transformation, where you interchange the two cycles. This.
Sorry, can I ask a question?
Yeah, sure.
So are we considering the bosonic states only?
Later, I will talk about the fermionic states. Here, it's just in general. It's just I'm just making some general claim about CFT.
But for fermions, the spins can be half integer.
No, not the spin. The spins are actually still integers.
Still integers.
Right.
Then are they odd number for fermions?
Because spins actually is L0 minus L0 bar.
Okay, so spins can be any integer for fermions.
Spin can be any integers for fermions. Let me see. I would say in principle, yes.
Okay, thank you.
Yeah. I mean, this is just a constraint coming from the T transformation. And moreover, we can have an S transformation, and this imposes constraints on the spectrum.
Sorry, one more elementary question.
Right, yeah.
In the velocity characters you wrote down on the right side, the product begins from 2 and equal to 2.
Right.
Why there is no n equal 1 in the product?
That's because L minus 1 annihilates the vacuum. Because L minus 1 acting on a state, it's actually a derivative of the state.
I see.
But the vacuum is translationally invariant.
Okay, thank you.
Yeah, so that's why we only have this. Yeah, that's peculiar to only the vacuum state. Yeah. Okay, are there any more questions? Okay, so let's continue. So the S transformation actually imposes constraints on the spectrum. For example, you can run the program of a modular bootstrap and try to constrain the possible spectrums appearing in the CFT. Okay, and now I move on to the rational CFTs. So by definition, rational CFT has only finitely many conformal primaries. And actually, this condition is enough to show that the C and all the conformal weights are rational. This is a very powerful result, or actually already known a long time ago. And some examples of rational CFTs could be like lattice CFTs or with models. And then I can write the partition function in the following way, because here we have only finitely many conformal primaries. I can express in terms of a vector times here the D times the characters. And now let's look at,
Is the opposite true? If all C and H are rational CFT are always rational CFT? Is
let
it
me see.
true? The opposite direction.
That's a very good question. Is this true?
Looks
Let me
like
see. Can I find some counterexamples? Yeah, it seems to me that's true. Yeah.
okay.
But maybe someone in the audience have some counterexamples.
Okay.
Okay. Yeah.
Okay.
Yeah. Okay. And so let's look again at the modular invariance. So now the T and S transform these chi-i's, so like as matrix acting on the vectors. And then so they need to satisfy this condition such that the T and S form representations of the SL2Z. And then you can try to classify all possible Ds such that this C is a modular invariant. But that's another topic actually, and this so I will not talk about that today. So in this talk, I will only assume D to be diagonal. I will call this a diagonal rational CFTs, a diagonal modular invariant. Okay, and then now comes the the important part of this talk, which is the observation that characters from this equation, they form a weight zero vector value modular form for SL2Z. Okay, so maybe you're not familiar with the notion of modular form. Let me just give you a quick recap. So given a function f with argument defining on the upper half plane, a modular form of weight k means that if you consider this transformation, and I get an atomic factor with a weight k here, and this matrix is in SL2Z. One example of a modular form, or one class of example, is the so-called Ising series, where basically you're just summing over all the lattice points on C, and actually you can easily prove that this is their modular forms of weight k. And for us, the important point is that, in fact, all holomorphic, so modular forms they naturally form a ring, and all holomorphic SL2Z modular forms they are freely generated by E4 and E6. So although they are complicated objects, their structure is actually very clear. And then the important thing is that characters, they are actually solutions to an nth order modular linear differential equations, which are abbreviated as MLDE. So this was actually shown already a long time ago. And from another point of view, you can understand this result from the presence of non-vectors in the spectrum, which was shown in this paper. Okay, so now let me explain what is an MLDE. So I'm sure everyone is familiar with ordinary differential equation. So here, the modular just means that we want to preserve also the modularity. So here, the d tau is a so-called serial derivative, which is basically a derivative of tau, but we need to add another term, k over 12. This E2 is where k equal to 2, but E2 is not a modular form, it's only a quasi-modular form. But however, if you make this combination, so that you can cancel some terms that do not transform modular covariantly, such that this d tau actually maps a modular form weight k to a modular form weight k plus 2. And also the coefficients here, phi a, they are modular form, so weight the corresponding weight, such that this expression should increase the weight by 2n. Okay, so this is our so-called modular linear differential equation. Okay, now so suppose naturally we are led to this question. So suppose we are given characters, how can we determine this MLDE? Actually, again, the solution is actually quite simple. Because this is very similar to an ordinary differential equation. We just use the Wronskian method, where I write down such a WK, where I express all the characters in the following form. And then it's easy to show that the phi k here actually can be just expressed in terms of WK over WN. Okay, so then you may say that, okay, so since we already know the structure of modular forms, then this must be very simple. But however, there's an important caveat, which is that here we have a Wn, the denominator. So in general, this expression would be meromorphic. So we have poles on the upper half plane. So now let's examine more carefully about the poles of this expression. So first of all, let's assume that characters have no poles in the upper half plane. So the chi-i's, they have no poles. This is reasonable because we know that the chi's are power series in terms of q, which is exponential 2 pi I tau. So if tau is on the upper half plane, this factor is exponentially small. So then naturally we expect that this will be a convergent series in the upper half plane. So this will not give rise to pole in WK. But it could be that there could be poles of F5K which come from the zeros of Wn. This is totally possible. So then this makes the story more complicated. So then we are led to the question that how can we constrain the zeros of Wn from our known information? The answer is provided by the so-called Valance formula. So here, to explain the Valance formula, let's first write down the fundamental domain of the upper half plane under the action FSL2Z, which takes this shape. So for every string theories, this should be very familiar. And this Valance formula is saying that for modular form of weight k, actually the order of zeros or poles inside this domain is actually related to the weight. So here k is the weight. And so first of all, we have from this picture, we have a cusp at I infinity. So we need to we need to sum over the order at I infinity. But we also have orbifold points, because if I identify, for example, for this point, if I identify this segment with this segment, actually this will create an orbifold point at tau equal to I. So we need to divide by the order of the orbifold point. Similarly for the tau equal to omega. And then I express the rest of zeros in terms of this form. Okay, so this is some well-known result from mathematics. Let's apply it to Wn. Actually, strictly speaking, Wn is not a modular form. But if you read the proof carefully, so this formula also works. So we can apply it to Wn.
Sorry, I have one question.
Right.
So here, so K is, you just look at the congruous subgroup of with weight K.
SL2Z actually.
Is it SL2Z?
Yeah, I'm always talking about SL2Z, right?
Oh, I see.
Yeah,
it's not
so
congruous
it's always,
subgroup.
Yeah, that's the next part. Yeah.
Oh, okay.
Yeah.
But
so
this K is just modular form of weight K, you mean?
Yeah. Which K? Sorry.
This K over 12 or?
The K is the weight.
Okay.
Yeah. So the modular form of weight K. So F is the modular form.
I see. Okay, thanks.
Yeah. So we can apply this formula to Wn, so because we are interested in order of zeros, so I put this part to the right hand side, and I move this part to the left hand side, and this part is this n times n minus 1 is the weight, and moreover, from the very definition of characters, we know the order at the infinity, so this is also part of information. So, and this gives this, and this part I call this L over 6. So in such a way that L is always an integer. Okay. So this is just a rewriting of the Valance formula. Okay, and then next we can, the idea of pioneered by Mather, Mookie, and CERN is that actually we can invert this whole logic around and try to classify possible rational CFTs using by the number of characters and order of poles given by this formula. And but okay, in general, a solution of a rational CFT of a MLDE may not have the correct properties that we want. So we we need to impose some constraints. So for example, the vacuum character must take this following form, where this one is because we only have a unique vacuum in the CFT, and AI must be non-negative integers because they come from characters. And also for the chi-I, here this is purely a normalization because we can have degeneracies for other primaries, but let's just normalize it to be 1. Therefore, all the AIs here, they can be rational numbers. But remember that this is because of normalization, the AI should have bounded denominator. So the denominator cannot grow indefinitely. And then we do some computer search or analytical analysis to find possible solutions. And the next step is to identify or disprove the solutions using some physical arguments. And in the same paper, they look at the second order holomorphic MLDs where L equal to 0. And recall that the modular forms SL2Z are generated by E4 and 6. So for second order, this is the most general form we can write down. And already this mu can be determined in terms of central charge in this way. And what's surprising is that they found that there's only a finite family of solutions by imposing the following constraints. And actually, this family is known as the MMS family. So let me explain what they are. So actually, the first one actually secretly is a Lie-Yang singularity. Although here we have a unitary theory, but if you write down the characters, actually it's a non-unitary theory, which coincide with the characters from Lie-Yang singularity. And for the rest, actually they are all level 1 Westminster models with the following Lie algebra.
I have one question.
Yeah, sure.
So when you say second order holomorphic MLDE with L equals 0,
right?
So E4 doesn't have a pole, which means
no, it doesn't have.
Okay.
It doesn't have pole. It only has 0.
Okay, but so the higher like a module for E6 and so on are
they're all holomorphic. Yeah. Sorry. By the way, so yeah. So here I emphasize that we're talking. So this is the holomorphic modular forms.
Okay.
Yeah,
but
they have zeros. Yeah, indeed. Yeah.
So does E6 have a pole or not?
No, it has zeros but no poles.
Okay, then can't you have like a d tau plus mu E6 instead of E4?
But the constraint is that sorry, let me. Okay, so
I
because
think I missed the point.
Yeah, because this increases the modular form of the weight by 4. So here this should also increase
this should be
weight by 4.
4. Okay, I see.
Yes,
So
yeah,
by constraints. Okay.
Yep, yeah. Sorry, yeah. Thank you for the question. Yeah, so this should have the same weight, and we have this family. Okay, so I'm here. Okay, and actually, this family of Lie algebras actually was already known by mathematicians, Svitanovich and Bilinear. So this family of, apart from this is the so-called, I think so-called intermediate Lie algebra that is very mysterious. So let's first neglect this guy. And this series of Lie algebras, actually the dimension can be expressed uniformly in terms of this expression, where this H check is the Diokoff number. And similarly, you can, there's some formulas, uniform formula for other representations. And in terms of physics, this family of CFTs also appeared in many other places, or this family of Lie algebras. So for example, they appear at the boundary of 2D modular bootstrap for a twist gap. This in the 2D, and moreover, if you know the minimal 60 n equals 1,0 SFTs, those Lie algebras, except the A1 and G2, they all appear as gauge algebras of those SFTs. In terms of 4D, the instanton moduli space of simply laced algebras in this list actually is the same as the Higgs branch of 4D rank 1 equals 2 SCFT. And due to the beautiful work by Beam, Rossetti, and their friends, actually this 4D SFT can be mapped to 2D chiral algebra. And the Schur index of this 4D SFT can be identified with the vacuum character of Westminster model at this negative level. And interestingly, the solution, these characters, they are also solutions to this MLDE, but now they describe non-unitary family. So here is a unitary family, but this can also describe non-unitary family of Wisdom-weighted model. Yeah, so this shows the power of this MLDE. Because
so what do you mean by unitary family? So this bracket unitary means it includes in non-unitary, you mean?
I mean, this family is because central charge is larger than 0. That's what I mean by unitary.
Okay, but Liang is not the unitary.
Yeah, so yeah, sorry. Here, Liang, I mean that although this is unitary family, but if you write down the characters, they coincide with the characters of the Liang singularity.
Oh, I see. That's
yeah,
okay.
so
Okay.
so actually secretly this is a non-unitary theory. Yeah.
Okay.
Yeah. Okay, and okay, that's so this appears in many places of physics and mathematics.
Sorry, shall I? Yeah, maybe.
Sure. Yeah.
So,
Right.
are you saying that this Liang theory is appearing here is unitary? Is that what you said?
No, I'm not saying they're unitary, but because in the Liang theory, so we have a vacuum and another primary, but actually that primary is has negative weight. So if you write down the character for the so Liang has 2 characters. If you write down the characters, they coincide with the characters for this theory. So secretly, you can view this Liang as some unitary theory if you switch the role of the vacuum and the non-trivial primary.
Switch. What do you mean by switch? I mean.
Yeah. So what I mean is that so for example, if you look at the chi0 for this theory, it is q to exponential minus c over 24. But actually, you can regard this minus c over 24 as the character coming from the non-trivial primary of Liang. You find that they're actually the same. And for the other conformal, for the other primary of this family, you can actually identify it with the vacuum of Liang. So I mean, you just write down the expression and you see that they're same actually.
So just I try to understand that
right.
This character cannot tell the unitary or non-unitary. Is that correct?
That's true. Yeah, absolutely. Yeah, absolutely. Yeah.
Okay.
Yeah, that's the point. Yeah, thank you. Yeah. Okay, so let's move on. Sorry, I'm a bit slow here. Sorry. So here I mean to show you some state of art for classification. For more information, I refer you to this review paper by Mookie. Okay. So now I'll talk about our work. So in some sense, this is most important slide of my talk, which is the idea that we generalize the whole story to fermionic theories. Okay, so let's first need to understand what happens if we have fermions. We all know that if the system has fermions, then we should specify spin structures. So the manifold should be spin, and we should specify spin structure for a given fermion. And for a torus, the spin structure means that we specify the periodicity condition of the 2 non-contractible cycles. Due to physical reasons, due to historical reasons, we call it anti-periodic condition NS, stands for Neveu-Schwarz, and periodic condition Raymond in the R sector. And here I show you the 4 sectors and how they transform under S and T. So this is so the T transformation acts the periodicity of this part to this part, while the S transformation exchange the 2 boundary conditions. So then you understand this picture. I just would like to make 2 remarks. The first remark is that the Raymond sector is actually still invariant under SL2Z. And the second remark is that the so among the 3 sectors, NS sector or NS sector is invariant under S transformation, which will be important later. And in terms of partition function, we can make a further decomposition in terms of different 4 sectors. We call this NS tilde R, and R tilde. And so the way, as we know that the way to change the periodicity around this direction is to insert -1 to the f, where f is the fermion number. And by the way, if the system has supersymmetry, the Riemann sector coincides with the Witten index. And if we have further fugacities, you can refine it. You can refine the Witten index, and you get elliptic genus. But in this talk, I will only focus on these three sectors. Okay, so now we decompose this further. Then the next thing is that we need to understand symmetries associated to each sectors. So it turns out that there's a beautiful connection to mathematics, of which are related to the level 2 congruent subgroups of SL2Z. So actually, so here I'm giving you the symmetry subgroups for different sectors. So actually, this is very easy to understand. For example, for this gamma theta, as I already told you that S is inside gamma theta, and T squared, you just translate once and back. So T squared is also a symmetry of this NS sector. And here I draw the fundamental domain for the different sectors, which take this shape. As a remark, notice that now we have another cusp. So we still have a cusp at I infinity, but we also have another cusp on the real axis for one of them. And you see that for the NS and S theta sector, T squared, but not T, is a part of generator. Well, for the R sector, the T is a generator. So there are some important observations. And now let's just repeat the whole story and try to write down fermionic MLDE. So now I have 3 MLDs instead of 1. But since they are transformed under each other by T and S, so still we only need to focus on one of them. And here the answers must be changed because we know that, for example, for the NS sector, only T squared is contained. So we are allowed to have half integers rather than just integers. And similarly for NS tilde. But for the Riemann sector, for the R sector, T is still part of the generator. So we are only allowed to have an integer in the exponent.
Sorry, what's T? Sorry.
T is just translation.
Oh, okay.
Yeah, the T in the SL2Z.
You mean T square includes T square as a symmetry? You mean?
Sorry, maybe I'm not very clear. So the T is just we have SL2Z.
Yeah.
And T is the part of one of the generator.
Yeah.
You add
so that
T.
That I understand. But when you said T includes T square means as a symmetry, you mean?
I mean the generator has T. I mean I just mean this. Yeah. So here the generators are T squared, but here is T.
Okay, as a symmetry. Okay, I understand.
Yeah. And I'm just saying that those sectors, they should understand, they should be invariant under their symmetries. Yeah. So this constrains the power of in front of Q. Yeah. And also we need to understand the ring of modular forms for different subgroups. And here I give you the result. And here theta i's, they are Jacobi theta functions of weight 1/2. And as an important remark, compared to the bosonic case, here we can have modular forms of weight 2. And it is not the quasi-modular form E2. So it's a modular form, general modular form under those subgroups. That's an important difference. And okay, and now let's try to find MLDEs for characters. And again, we have the problem of having poles in the coefficient, and we need a corresponding valence formula. So here I'm showing the valence formula for the NS sector. So I draw this fundamental domain. I repeat the fundamental domain I showed you before. And so this is the expression. And let me just give you a few remarks. So compared to the bosonic case, here I have factor 3 because those subgroups, they are index 3 subgroups of SL2Z. So we have this factor here. Well, on the left-hand side, first we have factor 2. Well, if you know the proof, that's basically because because T squared, but not T, is contained inside the symmetry, inside as the subgroup of gamma theta. And moreover, we also have another cusp centered around 1. Notice that we need to identify this with this. So actually, so those are the same cusp. And then we have some other contributions. Now let's apply this this expression to Wn again, and I can get this expression. Although this is so, let me first make a remark. So it turns out that the cusp at this point is actually related to the conformal weight of the remote sector. So although here I'm only talking about the inner sector, but if you write down the formula, you notice that the remote sector also plays a role in the formula. And similarly, I can define the factor this number L, which tells us the order of poles for the coefficients. So although this is like a straightforward application, but as far as we know, no one has written down such a formula before. So I attribute this formula to our paper. Okay, and as a first step of the classification program, let's focus on the holomorphic cases where L is equal to 0. Okay, and actually, as a warm-up example, we can consider the first order MLDE because here the elements of modular forms are bigger. So actually, order MLDE is already non-trivial, which takes this form. But here it's very simple. We only have one coefficient, which I can express in terms of central charge. And moreover, actually, we can make a change of variables, and where I define this lambda and bring this to this form. It's easy to show that this actually you can integrate this finesse and get an exact expression with the following form. And it turns out that to have non-negative coefficients, the constraint is that C must be K over 2. So that is to say, this family that we found for holomorphic first order MLDE actually is a tensor product of K equal to 1 theory, where K equal to 1. So then what is this, like this original theory? It turns out that this is precisely the Majorana fermion. Okay, and at this point, let me talk about some connection to bosonic theories, which is
sorry, Majorana fermion is just free fermion?
Yeah, Majorana free fermion. Yes.
Okay.
Yes.
Thanks.
Yeah. And let's talk about some relation to bosonic theories, which is the Ising model that we all love. So we all know that if you look at rational models that only have variotional symmetry, there's a well-known family of theories known as the minimal model, labeled by two integers. And if you want it to be unitary, they must only be differed by 1 with the following central charge. So I label by a single integer m. And in particular, m equal to 3 is the Ising model, okay, which describes the critical point of the, actually, I should say it's a critical point of Ising model. And with actually 3 conformal weights. And here I write down the expression for the 3 characters. And I also show you the S matrix for this. And it's easy to find a third order holomorphic MLDE, bosonic MLDE for the 3 characters. Okay, so why I'm talking about Ising model is because if you look at more carefully the solutions, so here I'm writing the solution for K equal to 1 for Fermionic MLDE in the following form. If you compare with the characters here, you notice that actually we just need to make some combinations of characters. So this is the NS sector, NS tutor sector, and the remote sector. And then you get the Majorana fermion. And moreover, you can make a consistency check for the S matrix. This S matrix takes this form, where you do S transformation, you just multiply this matrix to the character as a column vector. In other words, you have this expression. And it's important to notice that actually those 4 numbers, they are all the same. Well, those 2, they are different. And as a result, only if you take if you add chi0 with a chi epsilon, the result will be invariant under S, which is all consistent with the fact that only S is contained inside the NS sector, and this part will be cancelled. Okay, and this actually simple fact is I can lead to a few of physics, which is known as fermionization. So it's known that the Ising model, actually as a bosonic theory, if you gauge the Z2 symmetry, this is Z2 global symmetry in the Ising model, you get the Majorana fermion. And the Z2 symmetry actually is mapped to the -1F symmetry in the Majorana fermion. And you can even deform this theory away from critical points, and you can match phases, states, and operators, etc. You get the exact match. In terms of the disgauging procedure, more precisely, we can, so nowadays we have a modern understanding of this procedure. We need to couple the system to Z2 background gauge fields and the sum over all sectors or spin structures. So this is a huge field, and there are lots of papers. I'm sorry that I could not list all of them. I just list some big names in this area. But in order to explain this procedure, we need to, then there's a huge, you need to introduce a lot of techniques from algebra topology, which is actually very involved. But here, let's just be humble and work at the level of primaries. So I claim that the fermionization procedure is possible due to the presence of a Z2 symmetry current, a fermionic Z2 symmetry current. So here, the Z2 symmetry is reflected by the fusion rules. So this current is this phi 1/2, which is the epsilon. So here I changed the epsilon to 1/2 to denote the conformal weight. So if you compute the fusion rules of this guy with itself, you get back to the vacuum identity. And the fusion rule of this phi 1/2 with other fields, so if you fuse those with those, you always get only one field on the right hand side. So in the CFT literature, this is known as a simple current. So this phi 1/2 is a simple current, and this is a fermionic because it has weight 1/2. And if you know the technique of simple current, so you can use simple current to construct, starting from say a diagonal modular invariant, you can construct a non-diagonal modular invariant by regarding this simple current as some Zn conserved charge, and the charge is determined by the monodromy of the simple current around the field. So the right means the unique field that appear after the fusion. And if this expression gives +1, then the fields are in the NS sector. If it gives -1, then the fields are in the R sector. And then we combine the fields that appear in the same orbit. So this may sound very complicated, but so what I want to say is actually, so this is the modular invariant partition function for the Ising model. And here I'm just rewriting the expression in the following form. Here I combine these two fields because they appear in the same orbit. And here it's invariant under the fusion, so there's only one field here. And then actually we can, although I'm considering only these three sectors, we can get information for the R tilde sector, which is just to 0. But here you can prove this rigorously because due to the presence of a 0 mode. Yeah, so in some sense, we are just writing this partition function in terms of a more complicated form, a non-diagonal form. Okay, are there any question?
So could you remind me with the NS tilde?
NS tilde, that's the,
Yeah.
sorry, okay, so let me show you, that's this sector. This I call NS tilde. This is NS tilde, R and R tilde.
Just and let's say okay.
Right.
So in this partition function, you are saying that this. Sorry, no, not that one. This below, you wrote some NS tilde sector, right, in the partition function.
Right.
But
this transformation is basically trivial because you just change tau to tau +1, so you only get a minus sign here. So those sectors, they are trivial transformations in some sense.
I try to understand what the term generic definition of this is NS tilde sector. How can I?
It's just yeah. Okay, so but it's just what I wrote here. So this is the NS sector. This is NS tutor sector, where you insert -1f. So you change the periodicity along the time direction.
I see.
Becomes
Time
periodic.
direction. Okay.
Yeah, yeah. So this is space, this is time, right?
Okay, okay. Thank you.
Yeah. Okay. Okay. Is there any other question? Okay. So now I will talk about the 2-character case. Actually, in the case of 2 characters, the story becomes much more involved. So first, I read out the following MLDE, the general form, and before you do any computation, you can first do a quick check. You can express all the central charge and the conformal weights in terms of those parameters. We have 3 parameters here, and we found that you always get L equal to 0. So so everything is consistent. And moreover, we can try to, in order to classify MLDs, we need to express mu I in terms of C and H and S. But naively, because here we only have 2 parameters, but with 3 mu I's, there's 1 extra parameter in our problem. So we need to impose an extra constraint. So the constraint I imposed here, so in our paper, we mainly talk about two possible constraints. One is mu3 equal to 0. So you can say the motivation for this is that if mu1 and mu2 are, if those two on the contrary are equal to 0, we're back to the bosonic case again. So in other words, if I impose mu3 equal to 0, that's like the opposite of bosonic case, which is the case that we are really interested in. Another possible constraint is that, remember, the vacuum is inside the NS sector, and I express the vacuum character in the following form. And this A1 actually expresses the number of free fermions in the problem. But since we already understand well the free fermions, which arise as in the 1-character case, we can just set A1 to 0 to try to see something new. And let me repeat the strategy to find the characters. So again, we make power series ansatz with constraints. But here, in the NS sector, the difference is that we can have half integers in the exponent of Q. And then we do some computer search because we know that C and H and S, they are all rational numbers. We can make a bound on the denominator and try just to search in the computer software with the following constraint. And the second step is to identify or disprove the solutions. Either you can try to because a consistent CFT requires more than just torus partition function. This can be either we can either check the fusion rules, or another, as pointed out recently by this paper, there could be some extra constraint coming from the Riemann sector. And well, in other words, although they transform nicely with respect to each other, there could be more constraints from the Riemann sector.
May I ask a question?
Yeah, sure.
In the previous,
sure.
This simplest case, this Ising.
Yeah, right.
Yeah. So in the one page go back. Sorry,
back.
One page go one. Yeah, this
part?
The solution. Yeah, this one.
Yeah, right.
So okay, you obtained this bosonic minimum model.
Right,
I mean, from bosonic minimum model, you obtained this fermionic one, right?
Right.
By using some MLDE or some technique. How do you specify fermionic field theory from bosonic? By this. This one, yeah.
Yeah. So I would say that we are just trying to use some fermionic Z2 symmetry current.
Yeah, if we can specify this kind of current, then you can do some technique, right? To see how to impose boundary condition for and antiperiodic or periodic. But in this technique, how do you specify the fermionic field?
So let me see. So first of all, one intuitive way is to look at the conformal weights. So if the weights they are half integers, So we expect that this should be related to some fermionic current.
Okay.
For example, like the 1/2.
Right.
Yep.
Right.
Yeah.
Right.
Actually, yeah, it's a free fermion. Actually, it's a free fermion current.
Right.
Yeah, that's basically the strategy. Yeah.
But in the minimum model, not always have this 1/2.
That's right. That's right. Yeah. Yeah. That's why we can only do that for cases where we have the T2 symmetry.
Right.
We cannot always fermionize the theory.
Right.
It's only possible if yeah.
Then how do you know the Fermionic theory from your method?
That you need to yeah. One thing is to compare the characters. So yeah, that's involves some guesswork. So
guesswork.
Yeah, we find the solutions and we try to because for example, if we know the central charge and the conformal weights, so maybe we can make some guess and then we compare the characters. If the characters are the same, then there's already a very strong evidence that they're the same.
Okay, so you need to guesswork from your result.
Right.
Okay.
So the solution doesn't tell you which CFT it is. You need to guess. Yeah. Right.
Thank you.
Yeah. Right.
Since we had lots of questions, so don't worry about time. You can.
Oh yeah. Okay.
Time.
Yeah. Actually, yeah. So yeah. Sorry, I'm very slow here. Sorry.
Seems like you have more slides, so please, yeah, you can take your time.
Okay. Okay. Thank you. Yeah. Okay. So I'm finished this part. So let me present the main result of our paper, where we classify, where we give 6 families of fermionic solutions, consistent solutions to fermionic MLDEs. And of course, I have no time to talk about all 6 of them, although they are all very interesting. So in this talk, I will only focus on this family. So let me first explain why we call this BPS family. So BPS is just we set mu3 equal to 0. So the mu3 is this guy, this constraint. But it turns out that if I set this to 0, if I transform this equation to the Riemann sector, and in the Riemann sector, there's always a solution that starts with q to the power 0. In other words, in the Riemann sector, there's always so we have 2 Riemann sector primaries, and one of them always is equal to CO24, because our definition of character. Why we call this BPS is because when the system has a supersymmetry, if it's superconformal, and you can show that by looking at the algebra, the Riemann sector conformal weight must always be greater or equal to CO24. And if it's saturated, so we just borrow this terminology from 4D or 6D physics. If this is saturated, we call this like a BPS family in some sense. And we can further divide BPS family into 2 parts. One is without any free fermion, and the other is with free fermions. Okay, this is the family that I will talk about for the most of my talk in the rest. So here, let me give you a more detailed table of the family that we found. So let's identify them one by one. The first one is actually very simple. It turns out to be the INCOS2 super Virasoro model. It's well known that those models have the following classification. They're indexed by only one integer k. And for k equal to 1, the C is equal to 1. And if you look at the possible primaries, so by the way, if you have INCOS2 super Virasoro symmetry, we also have a U1R symmetry. So Q here labels this U1R symmetry as a U1R charge. So we have 3 states, 3 primaries. One is a vacuum, and the other 2, they have the same conformal weight, but different U1R charge. But if I turn off the viscosity associated to this charge, they have the same character. And indeed, you will find that the solutions of these 2 characters, a solution of this case, actually the characters that coincide. Okay, so this is good. Now let's look at the second one. The second one so remember in our classification, we have this central charge. If I plug k equal to 6, you can easily show that this actually has a 9/4. So then you may guess that this should correspond to n equals 2 super mini model with k equal to 2. So actually this k equal to 6, sorry, it's a typo. But in this case, the problem is that there are lots of conformal primaries because k is very large. And but still we can try to make a decomposition of those of the solutions in terms of the super velocity characters, super conformal characters. But it's a very involved, and so naturally, so we like to ask the question: Can we have a better understanding of this solution? Actually, the answer turns out to be yes. So let me first describe a bosonic theory, which is the SU2 Western model with level 6. So I promise that this is the most complicated theory I'll mention in this talk. And if you know the representation theory of Western model, or mathematically affine-class Moody algebra, so in this level 6 we have 7 primaries, and here the second label is for the affine node, because for affine-class Moody algebra we need to extend affine node to the ordinary SU2 Lie algebra, and they have the following conformal weights. And since here we have 7 primaries, so there should be a 7 by 7 S matrix. And again, let me write down the fusion rules in the following form. Here, I use ij to denote only the first label, because the second label is just 6 minus the first label. It turns out that this is actually very similar to the so-called decomposition rule of tensor product of SU2, the finite SU2 Lie algebra, but with one important difference, which is that for this part we have also 6 minus I minus j constraint. This is due to the presence of null states in this model, and this is good because if I plug j equal to 6, so this part is 6 minus I, but this part, if I plug j equal to 6, this is also 6. Let me see if there's a typo here. Yeah, but so if j is equal to 6, actually there's only one term left, and again we have we only have one field appearing after you take the fusion rules, and also for j equal to 6, it corresponds to this guy. This has conformal weight 3/2. So again, it's like a fermionic C2 symmetry current. Okay, and then let's try to understand again what fermionization means in terms of characters. And as I showed you before, the different sectors are determined by monodromy in the following form by this constraint. And since so here it's very simple, because here h is an half, this h56 is a half integer. So being plus or minus 1 just means that the difference is an integer or half integer. So I use this fusion rule, and I consider the fusion rules applying to each primaries, and then I can easily identify different sectors. For example, so in this guy, because the difference is 1/2, so they belong to the NS sector. And then because we are interested only in the NS sector, so we can reduce the full 7 by 7 S matrix to the S matrix only in the NS sector, and we get this table here. And you find out that so this is the NS sector. You find that chi0 plus chi6, chi2 plus chi4, they are precisely the two solutions to the fermionic MLDE. So from this point of view, we have an elegant understanding of the solution that we found. And moreover, if you compare the bosonic and fermionic partition function, we can actually make a guess about the R tilde sector, because if we want to have a diagonal modular invariant, and this turns out to be exactly actually a number 4. So somehow that's a hint that there's some supersymmetry in this fermionic model, apart from the observation that the characters can be decomposed in terms of equals to super conformal characters. Okay, so this is an interesting story. Okay, so why I'm talking about this? Part of the reason is that it's due to some construction in condensed matter physics. So let me let me give a side remark. So rational CFTs, they can also be algebraically described as a modular tensor category. So this is some complicated mathematical concept. But here, let me, so this is basic definition. But as physicists, we are trying to understand the definition in terms of physics. So I decipher all those complicated words in terms of physical language. Yeah, and the most important point is that in the modular tensor category, we should have a modular operation, which means that we should have an S matrix. And there's a beautiful formula first conjectured by Valance, which is the so-called Valance formula, where you can express the fusion rules. So this Nijk, their coefficients appearing in the fusion rules, they can be determined in terms of the S matrix. And moreover, recently, some physicists and mathematicians, they proposed the so-called Fermionic modular tensor category, which is saying that there's a Fermionic object F such that F squared, so F fused with self equal to 1, and we can use this Fermionic object to determine different sectors. And this is the expression they wrote down in this paper, where this S is the S matrix, and this Di, they are the so-called quantum dimension of the associated to each a primary. And epsilon I is equal to plus or 1 determines whether it's in the NS or R sector. So honestly, when I first look at this definition, I was very confused by this expression. So why this epsilon I must be a plus 1 or minus 1? But actually, there's this some like beautiful identity among the fusion rules and the S matrix, which tells us that this actually epsilon I is precisely the monodromy charge. So this actually is the same as this. So now, in this way, it's natural to understand the whole construction of Fermionic object. And the Fermionization I told you before, it can be basically the same as the so-called Fermionic modular tensor category.
I have a question.
Right, sure.
What's capital D?
Oh, sorry. The D is a constant. It's the square root of the sum Di squared.
Okay.
Yeah, it's just a constant. Yeah.
Okay.
That's the definition. Yeah, appear in this paper.
So you just look at some column or row at the F.
Right.
That is written in terms of all quantum dimension, up to plus minus. That's what it means.
Right. Exactly.
Up to constant.
Yeah.
And I don't understand the connection to these monodromies. Monodromy has I and J, but here indices have only I.
Right. Because here we have a simple current. So first of all, given an F, so first of all, this J is well defined. It's uniquely defined. And actually, the original expression is to express this the left-hand side in terms of summation over all possible k, for example, n, k, I, j, and all this charge and d. But since here we only have one field, so so the point is that let me see. What I want to say is that so the expression actually corresponds precisely to this monodromy.
Okay.
Yeah, because yeah. So let me see if it's like. Yeah, I can show you the formula later. Yeah. So sorry, at present it's not on top of my head, so I cannot tell you why they are equivalent. But I checked that they are equivalent.
Okay.
So what's the definition of this df left-hand side?
This d is the square root of sum over di squared. So basically, it's a function. It's made of a quantum dimension. Yeah. So this di, yeah, di. So yeah, because that's related to the quantum group. So people call this quantum dimension.
Okay.
It's just a name. Yeah. Anyway. Yeah. So d is the you sum di squared and take the square root, you get this d. It's a constant, yeah.
And what is the equivalent monodromy? Which one is the equivalent monodromy? What you
This
said?
epsilon I, sorry, epsilon I
is
the same as this guy.
And I think Satoshi asked what's the relation I and other index?
That's
right?
because there's a formula relating those the left hand side with this guy and di, and yeah, sorry, because yeah, now I don't remember the precise formula, but the upshot is that this epsilon I is the same as this.
Yeah, he would tell us later. So let him go.
Okay.
Yeah. Sorry. Sorry. Maybe I'm very slow here. Sorry. Okay. So and more amusingly, actually, in this paper, they talk precisely this model SU2WC model with level 6. And the fermion, as I showed before, can be identified with phi 6. And the procedure is precisely the same. You use this use monodromy to determine different sectors, and you get a reduced S matrix in the NS sector. And another interesting fact is that you can use, again, apply the Valance formula to get the fusion rules only in the NS sector. And you get this fusion rule, this fusion ring. And actually, according to the classification of fusion category, this fusion rule actually is not present in the bosonic MTC. So this is somehow unique to the fermionic modular tensor category. Yeah, that's actually that's just like a side remarks, but I would like to point out some connection to other areas or other physics. Yeah. Okay, so now let's move on. Are there any questions so far?
But what the SNS?
Oh, that's just the S matrix in the NS sector.
But doesn't it mix with other sector?
That's because the NS sector. Sorry, let me go back. The NS sector, the S is in this sector is invariant on the S.
Oh, that sector is invariant. I see.
Yeah, so that's why I'm always talking about the NS sector.
Okay.
Yeah. Yeah. So sorry, maybe I still need like 15 minutes. So is it okay, Satoshi?
Go ahead.
Okay. 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 So now let's talk about the other theories in this list. So this example actually can be realized as fermionization of 6-4 product. So this just this is due to some guesswork. We found that this is fermionization of 6-4 product of A1 with a model, but here with level 1. And if you look at the primaries of this theory, actually has the following primaries. And again, we have a guy here, 3/2, which can be realized as a fermionic current, a Z2 symmetry current. And there are lots of degeneracies because it's a 6-4 product. And actually, so because here the central charge is equal to 6, so naturally one may be led to ask the question: can this theory has n equals 4 supersymmetry? For example, for the nonlinear sigma model with target space K3, the central charge is equal to 6. So 6 is a necessary condition to have n equals 4 supersymmetry. But actually, this model happened to be investigated in a recent paper by Harvey and Moore, where they show that there's at least n equals 1 supersymmetry. But whether this has n equals 4 supersymmetry, it seems still not that clear. And for us, we also try to decompose the characters in terms of n equals 4 superconformal characters, the solutions in terms of n equals 4 superconformal characters. But due to some peculiarity of n equals 4 PPS n equals 4 superconformal characters, so we cannot make so there's no simple decomposition, and we are also not sure whether this has enhanced symmetry or not. Okay, that is this for this model. And now let's jump to the last one. So you may have noticed that for the last one, I use a bracket here. So this bracket actually means that the second solution doesn't make sense. So it is actually only a one character theory. The second solution doesn't have bounded denominator, so it cannot be regarded as a character of certain conformal primaries. So then what is this theory, and why we list this theory here? Okay, so now let me first address the first question. This C equal to 12 theory, actually, so first this is solution, which takes the following form. And a way to describe the theory is to consider T2 orbifold of 24 free fermions. So here, so minus 24 is to kill all the free fermion current. And another way to describe it is to start from bosonic theory of SO24 with simulated model at level 1. And it has the following conformal primaries. And you can again, so they each either of them can represent like a fermionic simple T2 current, and you can do the fermionization. And what's interesting for this model is that it has very large symmetry group known as Conway group, Conway 0, which has very large order. This can be shown rigorously as follows. So so here, I mean, this model has n equals 1 supersymmetry, and to generate a supercurrent with the correct OPE, such that we have n equals 1 supersymmetry, we take all possible combinations of those three halves primaries, and look at the possible combinations of absolute alpha, such that the n equals 1 super conformal algebra is satisfied. And this possible choice breaks this continuous symmetry to this large but finite group, Conway 0. This was shown rigorously by mathematicians in this paper. And another interesting fact is that this theory is conjectured to be holographically due to the pure n equals 1 supergravity in ADS3, as proposed by Wheaton. So maybe you're more familiar with his proposal that the Moonshine CFT is holographically due to the pure gravity in AD3. In some sense, this is like the supersymmetric version of his in this paper. Okay, and now I explain why I list this theory in this family. So that's due to some marvelous bilinear relation, which works as follows. If I take any theory in the list with tensor charge smaller than 12, sorry, and I consider the dual theory, which has tensor charge 12 minus the C, and I make this bilinear combination, the right-hand side always gives us the unique character for C equal to 12 theory. And here, this M is the number of primaries that have the same character. So for example, in this case, as I showed you before, for the non-trivial primary, we have a twofold degeneracy, but they which are distinguished by the U1R charge. So this explains the factor 2 here. And actually, such a kind of bilinear relation. So this explains why we place this theory here. And also, this such kind of relation also appears in bosonic theories. So let's go back again to the MMS family, which I list in the following form. And it turns out that there's also a bilinear relation that such that the left-hand side always gives the unique vacuum character of EA level 1, which is the 1/3 of J, where J is the Klein J invariant. So this bilinear relation, in some sense, is decomposing the one character theory into two pieces. And here you can think of it as decomposing the EA Lie algebra. So recently there's some investigation of this bilinear relation. So in this paper, they propose some generalized coset construction, and recently those authors they extend this construction to 4-point functions. On the other hand, this bilinear relation has some relation to Heck image of characters, which was explained in detail in this paper. Okay, and actually, there's a very famous one character theory, so which is known as the monster CFT. And now my next slide would to introduce the monster CFT and talk about how to decompose the monster CFT into two pieces. So to explain this, let me first talk about some history, which is known as monstrous moonshine. So mathematicians in the last century, they classified all finite simple groups in terms of several families. And there's one particular family that is finite, so there's no general pattern. And with the so-called sporadic groups, 26 sporadic groups, and they organize in the following form. And the biggest one is the so-called monster group, which has a huge order. And later, there's a very beautiful observation by Mackay and Thompson, which states that if you look at J invariant, subtract this constant, and then look at Q expansion, and it turns out that if you look at those coefficients, they can be decomposed in terms of irreducible representations of monster. So it seems that this monster CFT has something to do with this J invariant. And later, by three mathematicians, Frankel, Lapolsky, and Merman, they construct the CFT. Well, in their language, construct a lattice VOA on the Z2 orbifold of the Lich lattice with the partition function precisely this form. And they show that this CFT has the monster group symmetry. So this explains why this observation. So by the way, the Lich lattice is a unique lattice in 24-dimensional even self-dual lattices with no element of norms 2. Okay, this is the monster moonshine. And recently, people, so given this table, so naturally, so because we have those relations, we could think if we could use the monster CFT to construct some new CFTs that have those other sporadic group symmetries. Indeed, so the most famous example is decomposition of monster CFT in terms of Ising model and the twofold cover of baby monster, this group baby monster, which was pioneered by the work of mathematician Gerald Hone. And recently, this group of people, the group of people from KIAS, they look at other possibilities and they decompose the monster CFT into some simple CFTs and a new CFT that has sporadic group symmetry. And then an important clue is that the characters are satisfied by linear relations. And so as a side remark, for this pair, Ising baby monster, in a recent paper, they understand this bilinear relation in terms of Fermionization and geosu projection. And moreover, in this paper, they try to generalize this phenomenon to try to give like a mathematical description of this phenomenon. And their slogan is that we can try to uplift a monsterizer pair. We are given a subgroup of a monster group and the centralizer of the subgroup inside the monster to commuting sub-VOA pair. Such that they obey some nice properties. And as a particular example, if we take two elements in so there's a 2A conjugacy class in the monster CFT, in the monster group. If you take two elements, if you take the product, they always lie in the following 9 conjugacy classes, and they generate dihedral group. And there's an observation due to Conway that those 9 conjugacy classes have something to do with the fine or extended EA Dinkin diagram, where I place them at the nodes of the Dinkin diagram. And you see that the order coincides precisely with the class label of the affine EA Dinkin diagram. And they further decorate this affine EA Dinkin diagram with commuting subgroups, and they successfully found the coset VOAs for all those cases. This picture is taken from this paper. Okay, and that's the beautiful story for the bosonic case. And now, since we already have a Conway group appearing as a Fermionic CFT, we can try to do the same story. And also, thanks to the work by Johnson Fried, he identified all n equals 1 super conformal VOAs with symmetry group Suzuki chain subgroups. So Suzuki chain subgroups are the subgroups that are below the Conway 1 subgroup. And there are 8 of them in total. And we found that so we can list can go on, and we found that the characters in the NS sector all satisfy bilinear relations, and the 2 of them I already showed they happen to appear in our family of BPS family, happen to be in our list. And moreover, if starting from this group, Yanko group, the theory actually has more than 2 characters, and this is some work in progress. Yeah, actually, this is the starting point of our project, to be honest. Okay. Are there any questions so far about this story related to Moonshine?
When you say bilinear relation,
right?
So with respect to this 12, like
yeah, K, because this is a Conway. This has Conway group symmetry.
Oh, I see. I see.
Yeah, as I explained here.
I see. Yeah. Okay.
By the way, this is a double cover of the Conway 1. The Conway 1 appears here. Here, and also appears here. Yeah.
Okay. Okay. Yeah. I see.
Okay. Thanks. So and I also have some slides for the other families, but since I'm already out of time, so I will skip those 2 to the summary. Okay. So to summarize, we initiate a program of classifying fermionic rational CFTs starting from fermionic MLDE. And we classify all holomorphic 1-character theories, and we find several families with 2 characters. Moreover, we identify many solutions and study their properties. And for some future direction, we can extend to some other cases, like for example, with poles or 3-character solutions. This is some work to appear. So the main point is trying to find some good family, such as the similar to the MMS family in the bosonic case. And another direction is to to consider the Moonshine story, which is the Conway Moonshine, as I showed you earlier. And maybe a third direction is to understand the relation to fermionic modular tensor categories, or maybe classify fermionic modular tensor categories at low ranks. And also, it's known that those stories have a very interesting relation to 3D physics. So it may be also helpful to understand the 3D in condensed matter physics. And that's all for today. Yeah, thank you.
Thank you very much. Questions from audience?
I have a question.
Yeah, sure. Yeah.
You know, hi. Yeah. In 2D, we have this. A lot of fermionic system can be bosonized, or the other way around.
Right.
Like if we can bosonize the fermionic system, the result from the previous bosonic MLDE should be the same as your fermionic MLDE.
Yes, that's right. Yeah, but then you need to combine all the characters. So because here I'm only showing you the NS sector, but for fermionic, that's because for fermionic MLDE we can only look at a specific sector. But if you bosonize all the theory, then you need to consider all of the characters. Then it becomes actually a very big MLDE with very high order. Yeah.
I see.
So the simplest example is this the Ising CFT and the Mariner fermion.
I see. Thanks.
Yeah.
Any other questions?
I have one more question.
Yeah, sure,
can you use this fermionic, this MLDE to derive? I think all of it seems that all the examples you have is equals to supersymmetry or super conformal algebra or something.
Right.
Could you bootstrap this n equals 1 stuff? Can you bootstrap n equals 1 super conformal algebra from this Fermionic system?
I would say it could exist because actually, even though we found 6 families, but we impose constraints on the coefficients. So in some sense, we are only looking at some corner of the whole landscape of Fermionic MLDE. Yeah, it could be possible that there's some family with only n equals 1 super conformal symmetry.
I see. I think because for n equals 1, since there's no BPS sector, right?
Yeah, maybe
because,
there's related to this condition. Yeah, it's yeah, if you have n equals 2 super conformal symmetry, then this is automatically satisfied. Indeed, yeah. But for n equals 1, yeah, this is not necessarily true. Yeah, I mean this condition. I mean, yeah, right.
Yeah, for n equals 1, since there's no like this BPS.
We still have the unitarity bound. But we don't necessarily have the equality here.
Yes, because you don't have this Riemann.
Right, we don't have this spectral flow. This story, yeah.
Yeah, you don't have spectral flow. I see it.
Right.
Thanks.
Yeah. Thank you for the question. Yeah.
Yeah, thank you.
Okay.
Any other questions? Okay, if not, let's thank the speaker.
Yeah, thank you. Yeah.
I will stop recording and leave the